Institute of Basic Science in the Jong in Korea, and he will speak about int-amplified endomorphisms and their dynamics.
Okay. Thank you very much for the introduction, and many thanks to the organizers and especially Professor Shramov for the kind invitation. And this is my first time to go to Russia and to this beautiful town. I quite enjoy it. So first of all, I would like to briefly mention my plan for these talks. Okay. So basically, there are 3 lectures, and so today I will mention the motivation and give some examples. Is this fine for you to read? Okay.
Maybe a bit bigger.
Bigger. Okay. And and tomorrow I will talk about the focus on the case of Picard number 1. Okay. And in this case, I will talk about this endomorphism PN conjecture. I will explain this later. And finally, on the last day of my talk, I will talk about the general case, the Picard number greater than 1, but mainly focus on dimension x equal to 3. Okay, so this so-called the Fakhrudin conjecture. Okay, so now we go to the first part of my lectures. So basically, I will talk about 4 aspects. So first, let us consider this. Let me give you the motivation and examples to study this project. So we focus on a smooth projective variety X. I use the smooth projective variety over the field C of complex numbers. Actually, this topic is also interesting in other algebraic closed field of characteristic 0 or even positive characteristic. But for convenience, I will focus on the field C of complex numbers. And we consider a surjective endomorphism. Okay. And of degree greater than equal to 2. Okay, so if the degree is equal to 1, then this F is an automorphism. So basically, this will be included in the Surjective next talks. So, but here we consider somehow the counterpart. This is a non-isomorphic surjective endomorphism. Okay.
Is this finite?
Yes. Yes. So if this X is projective, then this automatically implies this F is finite morphism. Okay, so the question is, can we classify such pair XF? Okay, so this question is very easy if the dimension is equal to 1. So if the dimension X equal to 1, then it follows immediately from the Hui's formula that this X is either elliptic.
Sorry, we classify X and F such that?
Sorry?
We classify the pair X and F
Yeah.
such that?
The existence of F of degree greater than equal to 2. Because for there are a lot of varieties, actually, they cannot admit such F.
But you said this from this?
Yeah, we assume there exists such F.
No, follows finiteness of what?
F is finite. So this follows from the surjectivity. This is the property. Okay. Okay, so if the dimension X equal to 1, then this X is either rational or elliptic. So this follows immediately from the Huel's formula, ramification divisor formula. So this means if the genus of X is greater than or equal to 2, then you cannot find such kind of non-isomorphic surjective endomorphism. So for the surface case, if the dimension X equal to 2, it has already fully classified by Nakayama, even for singular case. Okay. But this question is widely open if the dimension is greater than or equal to 3. So some very interesting tools to study these questions I can briefly describe. Okay, some tools. So while the 3 typical fibrations, there are 3 typical fibrations from the viewpoints of algebraic geometry or birational geometry to study X. Okay, so the first is the Albanese map. Okay, and the second is Cordaro fibration. And the last one is the MRC fibration, so-called the maximum rationally connected fibration. Okay, so the Albanese map means that for such variety X, you can find some morphism to the abelian variety. Okay, this dimension of the abelian variety is the irregularity. Okay, and for the Cordaro fibration, this means you have some dominant rational map to some general type variety Y. And the other one is the MRC fibration. This means for uniruled projective manifold, you can modulo its general rational curves to obtain some non-uniruled variety. Okay. Okay, so this X is uniruled, means this X is covered by rational curve. And then you modulo all the rational curves, the general rational curves, then you obtain some non-uniruled variety, such that the fibers are rationally connected. And back to our problem, so all of these 3 maps are F equivalent. So the equivalency means up to replace this F by some power. So for this X to Y, so here you have F. And then it can descend to some holomorphic map on Y. Okay, but note that for this well-definedness of G, for this MRC fibration, we need to carefully choose a special MRC fibration. For general MRC, it only descends to a dominant rational map. But Nakayama showed that if we choose some special member of this MRC fibration, then this F can also define to an endomorphism of Y.
So the problem is that MRC fibration is canonically defined, but only as a rational fibration, only as a rational map.
Yes. But if we choose some graph, you take the graph and then you doing some operations, we can make this descended morphism to be a morphism G. Okay.
And can you also clarify? So apparently there's no problem with this with making G holomorphic in the Albanese case, right?
Yes. There is no problem because this is abelian variety. Yeah, right. This is the universal problem. Yeah.
Which are not regular.
Right.
And also
for the Cordaro fibration, basically this is just the identity, because up to a power, it should be of finite order. Then
I know the theorem that the pericanonical representation of the automorphism group is finite on Y.
Yeah, because it fixes it fixes this canonical divisor, and in this case, the canonical divisor is more or less big. So.
And is it the same for endomorphisms?
Yes, they are the same for endomorphism. Yes, this is you can require we can consider this reference by Ueno or Nakayama Zhang. Yeah.
But Ueno, I think, Ueno used the book by Ueno, right?
Yeah.
But I think he goes only the birational morphism case.
But yeah, but for endomorphism, I believe this is okay. Yeah, you can descend to some.
So once again, for endomorphisms, you mean that every endomorphism
Yeah, you first descend to
induces an odd morphism of y, right?
of finite order. Yes, of even finite
Because
order.
for it to be a finite order, it has to be of degree 1.
Yes.
Excuse me, can you recall what is Quadratic fibration?
It's a pure canonical fibration. So you
Yeah. Yes.
sufficiently large individual power of the canonical class.
It naturally acts on these global sections of the anti-canonical of the canonical bundle, and then it descends to the project. MRC fibration is, I explained, you modulo these rational curves.
Okay.
You correct all rational curves which you find on your variety. So you have some of the rational corrected fibers and the base which is not covered by rational curves.
Okay.
This thing you mentioned that we can do inverted vibration on the nose, not variation. This is in all dimensions or only in dimension 2 because it's every column?
You mean this dimension x?
Yeah.
This vibration is independent of dimension.
Yeah, but you said that you can choose a very special model.
Right. Yeah. That is also works for any dimension. Yes. Okay, so let us talk about some very simple example. So first, so we consider the projective space. Okay, so I use example A. So we consider this power map of projective space. So this means we use F1, okay? Pn to Pn. It sends these coordinates x0 to xn, to power q, okay, with this q greater than 1 integer. Okay, so this is a very classical map, and you can check the degree. Whenever this q is greater than 1, it's a non-isomorphic surjective endomorphism. Okay, so let us do more. So we consider this hi. We define this hyperplane as the 0 locus of xi. Okay. And then you can check. So surely this is an ample divisor. Okay. And then we consider this pullback operation on the xhi. Okay. So clearly this is qhi, because this. If we pull back this divisor, it becomes this xi power q equal to 0, so that this is q times this hi. Okay? And then you can use the projection formula to obtain this degree f1 equal to q power n. Okay, so let us consider another example. We consider this multiplication map of abelian variety. So I use F2. Okay. So for this map, we send this X. Because for abelian variety, there is a natural group structure. So we can for any point X, we can consider it's n times X. Okay. So for some integer n, and we require this n is greater than 1. And then you can easily check the kernel of this F2 is equal to this fixed origin 0. Okay, so this is the number of n torsion points so this is isomorphic to z modulo nz times 2 dimension n. Okay, because this is the C and there are 2 directions z. Okay. So then you can check this degree F2 is equal to n 2 dimension n. 2 dimension A. Okay. So because this is for the degree of the, a finite morphism, we just count a general point and then consider the number of its inverse image. But for abelian variety, it's always a tau, so you can consider any point its inverse image. Okay, so this is this degree. And also we can consider this pullback of some ample divisor. So this H2, I can use, actually this is linearly equivalent to n square H2. So, but here we need to carefully choose this H2. In general, this is just a numerical equivalent. But to make it to be linear equivalent, you need to choose the symmetric ample divisor, okay? Okay. So we can consider this example A and example B. So we find that for this linear operation, pullback induced by this pullback action, it always fixes this ample divisor up to a scalar, okay? So what if we consider this product? So let us consider example C. So this product map. Okay. So we consider this F1 times F2. Okay, let us consider this F. We use F1 times F2. Okay. So which is Pn cross A to Pn cross A. Okay. And then we fix an ample divisor H, which is just defined by this H1. Sorry, maybe this notation is bad, but I just fix H1, okay. X1. Let us just consider H1. Because there is one more H2, okay. So we fix this H to be P1 pullback H1 plus P2 pullback H2. Okay, these P1, P2 are the natural projections. And then we calculate this pullback of H. Okay, so this actually, it's not very hard to prove. It's linear equivalent to H plus Q minus 1, P1 pullback H1 plus n square minus 1, P2 pullback H2. Okay, so in this case, so sorry, I skipped the computation, but it should not be very hard because. Sorry?
What is U?
U. There is no U.
Okay, I
Like
see.
in the definition of F.
There is no U.
Yeah.
Q. No, Q is like an example.
Q is this Q, power map.
Okay,
This
okay,
Q,
okay.
sorry. Yeah, this is, I said this is the this scalar of this Q, yeah. Okay, so in this case, we cannot expect this pullback of H is a scalar of H anymore, but we can
N, the dimension of Pn, and the
sorry. Yeah, the notation is bad. You are right. Yes, I use M. I'm sorry. Yeah, this the notation is very bad. I should say. Oh, yeah. This is N. Still N. Yeah, this N is the dimension of the abelian variety. Okay, sorry.
But not the dimension of Pn.
Yeah. No. It's nothing to do with this. Maybe I use M. Okay, sorry. Maybe. Yeah, the notation is bad. I use M. Q power M.
Yes.
It's okay?
And so they are also.
So, okay. Yeah, thank you.
So N is dimension of abelian variety?
Yeah, N is the dimension of the abelian variety.
Why do you need to be the dimension of a given variety? It's just
No, I
multiplication of
think
the
it's multiplication. What we multiply by.
So you just multiply.
Why do you ever need to multiply by the number? Which
Ah.
is the dimension? It's also independent number.
Oh, so sorry. Oh, I understand. Sorry, you are asking about this N, right?
Yeah.
Oh, I'm sorry. Yeah. Then maybe I use another one.
No. Use another one for dimension of a given variety.
Yeah. Maybe I use this M prime. Okay. I'm sorry. Yeah, you are right. Yeah.
Just little dimension of A, dimension of A.
Yeah. Also, indeed, we don't need a dimension here, right? Because I just use the dimension A. Oh, sorry. Yeah. I'm sorry. So, is there any other confusion?
So what's the right formula?
Sorry.
Is the formula right?
Now the formula is totally correct.
Okay.
It's exactly the n, which is multiplication by.
Yeah, this N is the multiplication. This Q is the coordinate power map. Okay. Okay. Now, although this pullback H is not a multiple of H anymore, but we can see that the difference of this pullback h and h, this is still an ample divisor. Why? Because this q is greater than 1 and n is also greater than 1. So the sum of this guy is actually still ample. But this may be another ample divisor. But anyway, the difference of this pullback h and h is an ample divisor. So later on, we will see that for example A and example B, they are so-called the polarized endomorphism. But the product is not polarized anymore. But this belongs to a more general notion I will introduce later. Okay, so is there any other question for these 3 examples? Okay. So let me introduce our key notion. Indeed, there are some other examples. For example, the non-trivial Pn bundle over the abelian variety. But this, to write down that coordinate map is more complicated, so I will skip there. But this, I think this trivial product is more easy to understand. Okay, let us consider the definition. So we fix a surjective endomorphism. Okay, of normal projective variety. It's not necessarily smooth. Okay. So we say this F is polarized. If the pullback action on this H is linear equivalent to some Q times H. So for some ample H, okay, and Q is greater than 1, usually we make this convention. Second, we call this F is so-called the int amplified. If the pullback action minus this original H for this ample divisor is still ample.
And is it possible, so you say you make an assumption that Q is greater than 1?
Yes.
Is it possible that you have an endomorphism of degree greater than 1, which is polarized, and for which such a Q is equal to 1?
It's impossible. Because if the pullback H is just equal to H, then by the projection formula, this degree F has to be 1. Yes, yes.
So I mean that it automatically follows.
Yeah. So, but here I didn't assume the non-isomorphic. So maybe if we assume this is non-isomorphic, then automatically this Q is greater than 1. Okay.
What is the motivation of the definition? Okay, we have this example with F1 times
Yeah.
F2 such that pullback of some H is ample.
Yes. From this example, we find that this example does not belong to the definition 1. For definition 1, it's a very natural definition because if you just consider a smooth projective variety of Picard number 1, and suppose there exists such an endomorphism, then it's immediately this pullback H is numerical equivalent to some Q times H. Yeah. So, but not all of the endomorphisms are polarized. For example, what I mentioned in this example, so it's not closed under the product operation. So this is another motivation to introduce this second notion. But later I will introduce more motivation to study this, the second notion, so-called the int amplified. Okay.
By the way, it is something like monoid. I mean that we can take a product of two.
Yes. For int amplified, it's true. If you take the product of 2 int amplified endomorphisms, it is still int amplified. Yeah, this is one of the advantages to study this endomorphism. Okay. Okay, one more general notion is we call this F is amplified. If
maybe it's a stupid question, but how do you know that this example C is about second? We just have one ample.
Yeah, this H is ample.
Yes, but
and
we don't have another ample, right?
This H is also ample.
Yes, but what if we have another ample?
Yeah, here you can see this Q is greater than 1.
Yeah.
N is also greater than 1.
I mean,
Yeah.
what if we take not H, but another ample? So maybe.
Then this may not be true.
You need to find
We just find that there exists some H.
Amplified is that for some
Yes,
H.
but you say that it's for sure not the first. But
Not
we
for
don't know.
any H.
It should be for any H we have polarized means that.
No. For polarized, even for polarized, this means there exists some H.
Yes, but you say that C is not the example for the first. I mean, okay, maybe it's.
Yeah. For C, the reason is for polarized endomorphism, there is an equivalent condition is this pullback operation on the Nalon-Savory group always has modulus Q.
Yeah.
The same modulus, but clearly this is not the case for this situation.
Okay.
Yeah. But I will not introduce this. Yeah. But I just want to say this case is not polarized. Okay. Okay.
If Q equals n squared.
U equal to. You mean Q equal to n squared?
Yes.
Yeah. Then possibly I think it's true. Yeah. Then it's the case. Yeah. Okay. So one general notion is so-called the F is amplified. So we call F is amplified if this is still the same notion, F pullback H minus H is ample. But here, we don't require H to be ample anymore. So just the full sum H. Okay? Okay, so indeed, the third notion is more, how to say, after the notion of polarized is proposed, this amplified notion is first
For some H, not
for some general, for some not necessarily ample divisor H.
effective.
But we require the difference is still ample.
H is maybe effective or something like this.
No, there is no such assumption.
Okay.
Yeah. And also note that for this amplified notion, it could be an automorphism. This amplified could be an automorphism. But how to say, when studying this notion, people realized that it does not behave very well when running the minimal model program. So finally, this notion actually is introduced by my senior, and he found that if you further require this H to be ample, then everything becomes very nice. But in that time, there seems less motivation to introduce this notion. But with the time passed, currently more and more people realize that actually this notion have more motivations, which I will introduce from the dynamical viewpoints. Okay.
Can you explain what the int stands?
Yeah, this int means this H lies in the interior of the ample, the net cone. Yes. Yeah, so this is so-called this notion. So clearly, we can see this 1 implies 2 and implies 3. Okay.
Somehow easily stabilize amplified endomorphism to make int amplified.
Yeah. Sorry?
Can you somehow easily stabilize amplified morphism to make it int amplified?
Yes, there are some equivalent definitions for
like
this.
taking a product with Pn and making some.
But if there exists a non-int amplified component, then the product can never be int amplified. Yes. Yeah, maybe, because this situation is, actually this assumption is quite strong. It requires all the modulus of the eigenvalues is greater than 1. But surely this may fail in this situation. Yeah. So I should give some credit. So this notion is first introduced by Kringer and Rask. I'm sorry, I could not pronounce very correct. Yeah, these two mathematicians, and also Professor Fakrudin. And this notion is proposed by Shen Meng. And for polarized, I could not give credits because it's a very well-known definition. Okay. Well, the second part of our lecture today is about the dynamical degrees. But I guess tomorrow we will have more understanding. So we still focus on a surjective endomorphism. Okay. But actually, this notion for the dynamical degrees is proposed for arbitrary dominant rational map, not necessarily well defined. Okay. But for simplicity, today we will only consider this surjective endomorphism case of a projective variety. Okay, it's set up. And we fix the dimension of x is equal to n. And we also fix an ample divisor, h. Okay? Okay, now for each number p from 0 to dimension x, which is n, we can define the so-called the piece dynamical degree. I call the piece dynamical degree. Which is defined by dpf. Okay, so this is the limit of m tends to infinity. We consider its iteration f power m, pull back on this h self-intersection p times h dimension. Maybe I have already used the n, so I use n minus p. Okay, and then we take the mth root and let this tend to infinity. Okay, maybe this notion, if we first study this notion, then maybe it's a bit complicated. But so this p means before you do the iteration for this self-intersection piece self-intersection, and then outside. Because to define it to be a number, you need n pieces. So here, this is inside. Before after taking the iteration, we use this piece intersection.
What is L in the power of H?
It's P.
P. I'm sorry. Yeah, it's P. Yeah, and outside this pullback operation, there are n minus p times. Okay, and we take the mth root to obtain this limit. Okay. So some natural question is whether such limit exists, and also whether it really depends on this h or not. Okay, actually, both of the questions have already been answered. Okay.
Do we take the pullback first and then intersect divisors, or do we?
Yes, there is no difference herein. But be careful that if this f is just a dominant rational map, then this pullback action with the intersection usually do not commute. If this f is not well defined, just a dominant rational map, then this is the standard definition. We cannot do first the pullback and then make them times them. Yeah, this is the point. But here everything is okay because this is well defined endomorphism. Okay, so in another understanding is this dpf is actually the spectral radius of the pullback operation on the PP cohomology when x is smooth. Okay, so here I didn't write more carefully, but if for the compact Kähler manifolds or just the smooth projective varieties, this is just the maximum the maximum modulus of all the eigenvalues of this linear operation on the PP cohomology. Okay. Actually, you can. I think this is a linear algebra problem. I think at least for endomorphism cases, it should not be very difficult because this you can write down this matrix, and then do this computation. Yeah, this is just the maximum modulus of the linear operation. Yeah. Okay.
So you said that pullback and intersection commutes. When we.
So if this is the endomorphism, so this is just the FM pullback HP.
This commutes.
Yeah. This commutes. Yes. Okay, but in general, it may not be true. It may not be true. Okay. Okay, some remarks. So first, this limit exists and independent of the choice of the ample divisor is essentially proved by Professor Ding and Professor Siboni. Okay, so works of Ding and Siboni. And later on, but initially they're working on the analytic category, and then later on it's generalized by Chuang and Dang in the algebra setting, even in the positive characteristics. Okay, so by those works, such limits always exist and independent of the choice of H. Okay. So this is the first one. The second remark is this DPF are birational invariants. So this means that if you have a birational map x to y, okay, and you have the endomorphism F, or just the dominant rational map F, and then if you can descend to another endomorphism or another dominant rational map G, such that this guy is birational, or just generically finite is also okay. So if this is birational, then this means the piece dynamical degree coincides with the piece dynamical degree of G. Okay, so this is a birational invariance, or just the generically finite invariance. Okay. And the last one is, if you consider this P, we consider a function, send each integer P to the log dP. Then this function is concave. Okay, so the concavity means it satisfies dpf square is greater than or equal to dp minus 1f times dp plus 1f. Okay, so this is called the log concavity of the dynamical degrees. Yeah, but actually we will not use this in my lectures, but I think this is a very fundamental result, so I should briefly mention it. Okay. Okay, let us consider another notion. So definition. We say that F has a dominant topological degree. I use dt to represent the topological degree. So the topological degree means it's just the DNF. So the DNF basically means if you choose a general point from the downstairs and the number of inverse image, okay, and this is defined to be the topological degree. Okay, so usually we call the degree of F. Okay, so we say this F has a dominant topological degree if this DNF, or we just say this dt, is strictly larger than the other dynamical degrees. Okay. And by the log concavity, actually this is equivalent to, so by this remark 3, actually this is equivalent to this DNF is just greater than dn minus 1f. Okay, it's very easy to check. If you use this property, then this condition is equivalent to just the last dynamical degree is greater than the last second dynamical degree. Okay. Now, I will give some equivalent definitions for this definition and our previous definition. Okay. So the theorem. Okay. So this is by Shenmeng in 2020, and also an observation due to Matsuzawa. Okay. So we consider a surjective endomorphism F. Okay, this is just a surjective endomorphism of a projective variety. Then the following are equivalent.
I'm sorry,
Okay.
about
dpf squared
Yes.
greater than dp minus 1f times dp plus 1.
And speaking about the inequality for p is equal to n.
We only consider this p till n minus 1.
N minus 1.
Yes, yes,
Ah, okay.
yes. And we define this d0 always to be 1.
Yes.
Yeah, then it should be fine. Okay, the following are equivalent. So the first, maybe it's better to write here. So the first is f is int-amplified. So recall that this notion means the pullback on this ample divisor minus h is still ample for ample h, for some ample divisor h. Okay. The second is for every endomorphism f, it has a natural operation, linear operation on the Nylon-Savary group. Okay, so I use this n1x to represent this Nylon-Savary group tensoring the coefficient r. Okay, so these have all the eigenvalues of modulus greater than 1. Okay.
So you say n prime of x is Nylon-Savary group
Tensoring r,
What is r?
the real coefficients, to kill the torsion. Yeah. Okay, and also finally, this f has dominant topological degree. And in this, so as I mentioned here, by the law of concavity, this means the last dynamical degree is greater than dn minus 1f.
What does the second condition mean? All equivalent.
Yeah, so this is by the law of concavity, we can obtain this property. Okay. So this means this, actually initially in his theorem, he gives the some equivalent condition except the last one. And it already gives some interesting characterization because it relates to all the eigenvalues of this linear operation on the Nylon-Savary group. But later on, an observation due to Matsudawa told us that it has also a very strong connection with these dynamical degrees. Because in this case, the periodic points and also the orbits have very interesting behavior under this assumption, dominant topological degree. Okay. So this is the second part. Any other question?
By the way, I'm thinking about the last inequality, and d1 is bigger than 1. Bigger. It's never equal.
It cannot equal to 1, yes. It cannot equal to 1. So easily, how to say? Yeah, this is very important. For example, if you consider the product map, G and H, you take this to be, for example, P1 cross P1 to P1 cross P1. Okay? And suppose you take this G to be identity or just automorphism. So for example, you take this degree G equal to 1 and degree H is greater than 1. Then this F cannot be int-amplified. Although it has a component to be the polarized part. So this also answers your question. So for example, in this case, if F is int-amplified, then both G and H have to be int-amplified. Yeah. So in this case, if the degree G equal to 1, as you said, there are some eigenvalue is equal. The eigenvalue is equal to 1. But it cannot happen if we assume this condition. Yeah. Yeah. Thank you. This is a good question. Let me check how much time. I have 45 minutes. Okay. Okay, let us continue to talk about the properties of intemplified endomorphisms and its structural theorem. Okay. So if the variety X admits an intemplified morphism, then what can we say on its geometry? So a very important theorem gives the strong restriction on the singularities of the variety. Okay, so this is due to Bronstein and Hurin in 2013, and also later by Shen Meng in 2020. So we consider a pair XD. So this XD is just a pair. So this means the canonical divisor Kx plus D is Q Cartier. Okay. And we consider an endomorphism X F from X to X. And this is such that this is intemplified. Okay. So assume this D is totally invariant. Okay. So this means, oh, sorry. So maybe I further assume this D is reduced. Okay. So we're given a pair XD with this boundary D reduced. And we consider an endomorphism X to X such that it's intemplified. And assume this D is totally invariant in the sense that this F inverse D is equal to D at a set. Okay. So note that this D can be 0. So in the simple case, if D is 0, this just means if the canonical divisor is Q Cartier, this X is Q Gorenstein, then suppose it admits an intemplified, then this pair XD is log canonical. Okay, it has at worst log canonical singularity. And indeed, an observation due to Moraga recently, even if we do not assume this pair is Q Cartier, we can still obtain this assumption, this conclusion up to a small Q factorization. Yes. So in this case, if this X, we don't assume it's Q Gorenstein, then if we take its Q factorial model, then we can lift this F to its model so that up to this Q factorial model, we can obtain this such kind of singularity as a conclusion. Okay. So another interesting observation is. Oh, sorry. Sorry, I didn't explain this. So basically, this means if you take a log resolution, okay, so you have this, you take any log resolution. So this is log resolution. And you have this Kx tilde, how to say, it's a pullback of, sorry, it's not F. Pi pullback Kx plus D. And then you have some log discrepancy. And then it requires this AI are greater than or equal to -1. Yeah, this is the definition for the log canonical. Oh, what's? It's okay. Okay, sorry. Okay, another theorem. I just want to briefly mention some properties of this endomorphism. Okay, so this is due to Fakrudin in 2003, and later on extended by Professor Ding and myself in 2023. So we consider an amplified endomorphism. So this is an amplified endomorphism of a normal projective variety X. then the set of periodic points. Okay, I use this PERF to represent the periodic points of this F, in the sense that there exists some integer m, such that this fmx equal to x for this point. Okay, all the sets. So note that the periods may not be the same. Okay, I just use it, once there exists such some m, then it belongs to this set. Okay, so the periodic point is countable and Zariski dense.
What does
Sorry? This means periodic points. So, okay, so P.
The most straightforward sense.
So this means you consider you take all of the close point x such that fmx equal to x. There exists some m. Okay. Is there any confusion?
No.
Okay.
So it's both to count is a kind of small, and there is kind of
Yeah. Right. So actually, this how to say? Yeah, at least for the inter-amplified morphism, this is immediately can be proved. So how to show?
What's the idea?
Actually, the idea is suppose this is uncountable. Suppose that it is uncountable, and then you take the then you can take some you take the closure. Then there exists some component such that the restriction to this component is identity. But this cannot happen for this amplified, because for amplified.
If it's uncountable, then
Yeah. So if this is ample, and then and suppose you have some subvariety such that this is identity on Z, and then you restriction to Z, you obtain this identity H restriction to Z minus H minus Z. This is 0, but it cannot be ample. So this is the idea.
And what's the idea of density?
Yeah, density is more involved. It's required some equidistribution for this in the sense using these dynamical degrees. Yeah, but I think for the Fakrudin's proof, he may use some other approach, maybe positive, use some p-adic approach. But I'm not very familiar with that part. Yeah. But I think this is the idea. Yeah, you are right. Yes, but I from my part, I'm sorry, I'm not very familiar with this part. But this is. But from the complex dynamics, we can prove this Zariski density. But this is just this result is due to Fakrudin. Okay. So what we did is, if we consider this, if f is further inter-amplified. Then we can explicitly give this form of the point growth. Okay, so this means we can count this x such that this fmx equal to x. So this means the period m, the number of period m periodic points. Okay, so this is equal to dnf power m and 1 plus small o1 whenever this m goes to infinity. Okay, so if the m tends to infinity, then this kind of these points is has the same growth with respect to the last dynamical degree. Okay.
Can you remind me once again? Inter-amplified implies that the
Yeah. This
greater than
implies
one, right?
this implies we can further give this.
Yeah, inter-amplified implies that the dynamical degrees are greater than 1.
Yes. The last dynamical degree is the largest one, the largest dynamical degree. Yes. And actually, this is a conjecture of Shou Zhang. This conjecture in 2006. This is a conjecture. Yeah, so this is also some interesting property deduced from these inter-amplified endomorphisms. But indeed, in our proof, we focus from the viewpoint of a dominant topological degree whenever it is just a dominant rational map. But at an immediate consequence, this inter-amplified morphism gives us this kind of result. Yes. Okay, now let us turn to the main part of this lecture. Okay, so I will going to talk about these structural theorems. Okay, this is due to a lot of people, maybe at least a few, Meng and De Qizhang, and also Meng himself, and also Yoshikawa. Okay. So we consider a Q factorial projective variety. So X is a Q factorial. So Q factorial means for any Weil divisor, it's there exists some integer such that this multiple becomes a Cartier divisor. Okay. So Q factorial projective KOT variety. And such that it admits an inter-amplified morphism.
Say again, the word projective.
KOT variety. Yeah. So you can see this structural theorem is still not in the general form, because we said that this in this case by the Bronsted-Hurwin's result, actually it has log canonical singularity. But for this structural theorem, currently it only works for KOT singularities. So this general log canonical case is still unknown.
So KOT is the same as log canonical, but with strict inequality.
Yeah. KOT means the strictly greater than -1. Yeah. The discrepancy. Yeah. Okay, then, so the structural theorem told us there exists a quasi-Étau cover. So quasi-Étau means the morphism is Étau away from a codimension 2 subset. Okay. So there exists a quasi-Étau cover. I use this x tilde to x, such that I draw the picture. So this is our initial x, and this is our quasi-Étau cover x tilde. We can lift this f to the endomorphism f tilde, which is also inter-amplified, such that this the Albanese of this x tilde is also equivalent. We can descend this f tilde to an endomorphism on the variety, on the abelian variety A. Okay, so this is its Albanese, and they show this the Albanese map is a final type over A. So this means there exists some boundary delta, okay, such that this x tilde delta, it has KOT singularities, and this minus anti-canonical pair is ample over A. So this means if you restriction to the general fiber, then it becomes an ample divisor. Okay, so this is the definition for final type over A. So usually the absolute case for the final type means there exists some boundary such that this is KOT singularity and its anti-canonical divisor, anti-log canonical divisor is ample. But for the relative version, if the final type over A means you restriction to the general fiber, it's final type. So so as an immediate consequence, it means this Albanese map is also a maximum rationally connected fibration, because the final type variety is always rationally connected. Okay. So from this structural theorem, you can see the two fundamental building blocks. One is the abelian variety. The other one is the rationally connected variety or final type variety. Because up to an Étau cover, you can decompose this variety x tilde into two parts. One is you modulo this rationally connected part as the fiber, and the base becomes the abelian variety. So these two are the fundamental building blocks. So this is the reason why we need to study the inter-amplified morphism of the rationally connected variety. Because the abelian variety, the structure is already very clear. So the remaining big problem is how to understand the fiber of this Albanese map.
So like very informally, example C is something like not very far from the general case. Yes. An example C.
Yes. This is the motivation I mentioned this example C, because for this example C is just the we can imagine this as the PN fibration over the abelian variety. So this is quite similar to this. This is more general in the general form, extract from this example C. Okay. Sorry?
This doesn't tell us much about special fibers of opponents.
Yes. It did not give the description on the special fiber, but if we assume X is smooth, then I can show this Albanese is already smooth. Yeah, this is already a smooth fibration. If we assume X is smooth, it's not very hard to prove this structure. But even for the smooth fibration, currently I could not show it's locally trivial. Yeah, this means I'm not sure whether there exists some non-trivial deformation. Yeah, but it's already said that every fiber, yeah, we can.
Expect this.
Yes, I think we can expect this situation. Yeah. So immediate corollary is the corollary due to Yoshikawa.
Sorry, do we have like really non-trivial examples when okay, leave alone locally trivial, but at least when this fibration is non-trivial, it's not a direct product.
Sure. For example, this rule surface over elliptic curve.
Rule surface over elliptic curve.
Yes. I think there exists, for example, if you consider this O plus any L, and it's an elliptic curve, it's elliptic, and they always have int-amplified morphism.
Like regular endomorphism.
Yes. Yeah, I think in the paper of in the same paper when Shou Wuzhang proposed this conjecture, he classified all the rule surface which admitting this a polarized endomorphism, and this is one of the cases. It's not it even admits polarized endomorphism. Yeah. Okay. So from now on, in the remaining part of my lectures, I will focus on the following assumption. So if we consider X is a smooth, rationally connected projective variety, and suppose there is an int-amplified morphism, then X is phenotype. Yeah, this is immediately deduced from this structural theorem. Because if this X is rationally connected, smooth rationally connected, then it cannot have any non-trivial étale cover. So this X is just X tilde itself. And then for the rationally connected variety, it has vanishing irregularity, so that this Albanese is also trivial. So this means this X is just its fiber. So this itself is phenotype. Okay, so this is a very striking result. Okay, so now I will enter into the last part of my talk today. Okay, good. So finally, about the open questions. So the following several questions is what we would like to discuss in the following lectures. So the first conjecture, A. So this is proposed by Meng and also myself last year. So we are interested in this structure, okay? Under the assumption, with the assumption of maybe I use theorem star. such that, or maybe not such that. Such that X is smooth.
What is that?
This theorem. Okay. And we expect, there exists a tau cover. X tilde to X. Such that this Albanese, this is a smooth toric vibration. Over A.
What's the toric vibration?
Toric variety, yes. So, indeed, we would like to say more. So this means there exists a boundary divisor D, reduced boundary divisor D, such that this X tilde D restriction to every fiber, this is a toric pair. Yeah. So this means we would like to find a uniform boundary divisor, so that it's a restriction to every fiber. It's the toric toric boundary of this fiber.
And can you verify? So these toric varieties, they don't vary, right? So at least all the fibers are going to be isomorphic to each other.
I'm not very sure. I think for Hilbert surface, for example, this F2 and F0.
No, they can degenerate, but at least the generic fibers are isomorphic to each other.
Yes, sure. Yes.
Like, of course, the Hilbert surface can degenerate with.
Right. Yes.
Another way around, the 0 to F2.
Yeah. So I mean, in this case, we would like to find a boundary divisor for which its restriction to each fiber is the toric boundary. Yeah. But I'm not sure whether that will happen in this case, because this is a compactor. It's over the abelian variety. So usually for abelian variety, it does not have some totally invariant subset. So I suspect maybe this case cannot happen in this situation.
Can you once again? So why do we need a pair at all? So your claim, the conjecture is independent of any pairs or whatever.
Yeah.
Why do we want to have a pair here?
This is just the definition of this toric vibration.
But once again, the toric vibration is a vibration whose fiber is a toric variety.
Right.
No pair here.
Yeah, right. You are right. But I mean, in this case, in our previous definition, we are in a strong sense. This means, maybe this notion is not uniform. But I would like to find a boundary divisor D, okay, such that this X tilde D to each fiber F is toric for every fiber.
But
okay.
No. And also something happens. Maybe the pair is amplified or something. Otherwise, can you just take the total toric boundary and?
In some special case, we can achieve this situation. For example, we proved this conjecture under the assumption that if this X tilde has totally invariant ramification, if there exists a divisor outside which this endomorphism is a tau or quasi tau.
Do you mean that D? What do you mean also require from D?
This is effective D, reduced effective.
Does it behave well with respect to the endomorphism, or?
No, here I didn't assume this D is F inverse invariant. But if there exists some divisor which is F inverse invariant, then this is.
But why isn't this definition with D? Why isn't it equivalent with to a more simple definition? A simple definition. A toric vibration is a
or even we just consider every fiber is toric, then this is not unknown. Yeah, this is also a.
But it's equivalent to your stronger requirement, right? Suppose that every fiber is toric. Every fiber contains this toric boundary. take the union of toric boundaries over all the fibers.
I
It's a
see.
dimension one subvariety which
But I was thinking
restricts to the fiber.
maybe there exists some counter example. Yeah, I think there exists some example like this. If we consider this quadric fibration, and general fiber is P1 cross P1, special fiber is the cone. Then I was thinking maybe in this case we cannot find a uniform toric boundary. I'm not sure, but anyway, yeah, this we can. I'm not currently. I'm not sure they are equivalent. Yeah.
Once again, toric vibration means that we have like if we restrict to the fiber, we have toric variety plus the device is stay invariant or something.
Yeah, it's invariant with respect to the toric action. Yeah.
Yeah.
Yeah, this is the definition for toric variety. Yeah, yes. But yeah, sorry, but maybe I introduced the confusion. So for simplicity, we ignore this boundary. Okay, we just.
But still, do you does it also include the requirement that you have an action of a torus on x twiddle, on x tilde, such that it restricts to?
I think so.
fibers?
I think so. Yes.
So it's not just every fiber is a toric variety with respect to its own.
Yes.
torus,
Yes.
but,
There is a uniform
torus.
action. Yes. Yes. Right. Okay. So from this conjecture, there are several important cases. Okay. So also remark. So this conjecture is true
I'm sorry, I don't understand.
if.
What is the problem with the definition? Smooth progression over A, and what does it say about it? You have a discussion with Kostya about smooth progression over A. And what does it mean?
Sorry, I'm not very sure.
Because there is a toric action on the whole x twiddle, an action of a torus of the dimension
Of X?
as the dimension of the fiber, not of dimension of x, the dimension of the fiber, which restricts to a nice, good toric action on every fiber.
You mean that,
That's the additional requirement. I think it's exactly equivalent to the requirement about the
Yeah.
process.
what is this fiber over A? So we say that
All the fibers in particular, every fiber is a toric variety.
Yeah, every fiber is toric variety.
But the requirement that there is a uniform action of a torus is stronger than the
Yeah,
requirement that
yes.
the fiber is a toric variety.
Yeah, on x tilde. Yes. Okay, so this conjecture is true if we consider this situation. If there exists a boundary D such that xd is a pair and f inverse d is d, and away from xd, away from the support of d, this is quasi tau. Okay. So I think in the last workshop held here in last December, I discussed this situation because in that time the motivation is to solve some arithmetic conjecture, and we reduced to this situation finally, and then we established this structural theorem. So this means if there exists some reduced divisor D, such that away from this D, this f, the endomorphism f is quasi tau. There is no more ramification divisor, and this D is totally invariant. Under this assumption, then this conjecture is true. But actually, this conjecture, there are too many assumptions here. So the motivation is when we run the minimal model program, we finally reduce to this situation, and then we need to classify the structure. So this is the reason that we want to extend this to the general conjecture A. And another thing is, so from this conjecture A, an immediate conjecture is this conjecture B. Okay, so this is the Fakhrudin conjecture. Okay, so the Fakhrudin conjecture asserts that if X admits a polarized or intemplified morphism, so if this is an intemplified anamorphism of a smooth projective variety, of smooth rationally connected projective variety, then X is toric. Okay, So this is a very hard conjecture. So if there exists an inter-amplified morphism of a smooth rationally connected projective variety, so this coincides with the fiber, okay? Just you take A to be trivial, just a point, then X is toric. So this conjecture is only known up to dimension 2 by Nakayama. Even in dimension 3, there is no complete solution, okay? So I will talk about this conjecture on the last day of the talk in dimension 3, okay? And just one more thing is, okay, conjecture C. So this is, I call it the endomorphism PN conjecture. So this is what we would like to discuss tomorrow. Okay, so this is quite a folklore conjecture. So if F is a non-isomorphic surjective endomorphism of a final manifold of Picard number 1. So if this is a final manifold, X is a final manifold of Picard number 1. Okay, and such that this degree F is greater than or equal to 2, then X has to be projective space. So this conjecture is famous since last 80s, okay, in 1980s, yeah. After Professor Lassas failed some works, and then it becomes, it becomes a popular conjecture. But it's only known up to dimension 3, yeah. So this is the reason that we study conjecture B for dimension 3. In high dimensional case, I think I'm not very sure whether this conjecture is true. But for dimension 3, it turns out that it is likely to be true.
What do you assume about F? Nothing? No amplified?
Yeah, because for Picard number 1 case, any... For Picard number 1 case, any non-isomorphic surjective endomorphism is automatically polarized or inter-amplified. Yeah.
Can you, about conjecture B, so, okay, you have a toric variety, and what's another direction of this?
Yes, it's always true. Another direction is always true. For a toric variety, we can always find the and yes, extended by the. Yeah, right. It's actually it's extended by the morphism and multiplication map on the algebra torus. We extend it to the.
And this is it actually polarized or inter-amplified?
Yeah, it's polarized. Yes. I think the converse direction is in terms of the coordinates is explicitly written in Nakayama's paper, and I think later on I also give some explanation of this converse direction. Yeah. Okay. So surely we find that this.
And also, does this conjecture include that? So once again, if it's amplified, then X is toric, and in this case there exists another endomorphism which is actually polarized. But does the claim that F itself is polarized? Variety, do you have int-amplified?
Yes. For toric variety, we have int-amplified but non-polarized endomorphism. For example, as I say, and then we take one eigenvalue is 2, the other eigenvalue is 3, then it's int-amplified but not toric, but not polarized. Okay, so surely we find that this conjecture A implies conjecture B, and also implies conjecture C. And this conjecture C is we would like to talk tomorrow, and this we would like to talk the last day. Okay, so to conclude my talk, how many left? Okay, 10 minutes, good. So finally, I will introduce an independent conjecture. So such conjectures are very helpful when studying this formal conjecture B and C. So we call this is the totally invariant conjecture. Totally, maybe I use the linearity conjecture. Linearity conjecture. So for the conjecture B and C, we are wondering whether this X itself is projective space. But suppose it is projective space, the structure of this F is still very complicated. Okay, for example, if we consider such a conjecture. Okay, we consider a an endomorphism of a projective space such that its degree is greater than or equal to 2. And suppose, as I said, somehow like this totally invariant ramifications in this case. Okay, suppose there exists some, suppose there exists some reduced divisor D such that this D is completely invariant. Okay, so this means the set theoretically its inverse image is itself. Then the conjecture says this D is the union of linear subspace. Okay, so this is also a very hard question. So this means not just the invariance, but totally invariance. Okay, totally invariance. And also the main issue is we do not know the singularity of this D. We do not know the singularity of this D itself. So for this conjecture D is very helpful when we study this conjecture B and C, which I will briefly explain maybe on the last day of the talk. So for this conjecture, because later on we will not talk much about this conjecture. So this is only known for, I think, dimension 2, and the divisor case of dimension 3. So means if this is a threefold, it's a three-dimensional projective space, and there exists a divisor which is totally invariant, then it's linear. This is due to the Hurin and also Nakayama-Zhang. But for the curve case, even in dimension 3, for P3 to P3, and suppose there is a curve which is totally invariant, then whether this curve is linear, it's still not known. Yeah. And for smooth hypersurfaces, this conjecture is also known, but in general, very few things are known. Yeah. But this conjecture is crucial to study this B and C. So this is the summarization of this.
Do we get it right that conjecture A immediately applies conjecture B, and conjecture B immediately applies conjecture C, right?
Yes.
Just the vibration is over.
Yes, exactly. Yes.
Conjecture D.
But this is independent of the, this is another independent problems. So I think for conjecture D, it's more interested in the study of complex dynamics. Okay, so for complex dynamics mathematicians, they are more interested in this conjecture. Yeah. Okay, I think I will stop here. Thank you.
Are there any questions or maybe more conjectures?
This conjecture D is somehow related to some kind of standard form of endomorphisms, say, like, in the sense that there's like usual whole problem about tameness of automorphisms of A, and say here we can ask whether like there's some standard form of automorphism which kind of like applies some polynomial in one variable, and then we conjugate it by some automorphism and apply some polynomial. Do you know what this is called?
So sorry, could you explain?
Is it related to existence of some standard form in terms of generators of monoid?
You mean the logarithmic differential forms?
No. Okay, maybe I'll ask you that later.
Oh, okay, sure.